What's the agenda today? All right. Sorry for the delay, guys. Got caught up with something, and but yeah, we are here. The third live stream in the Road to 10x live stream series, and today's one, going to be diving deeper into live streaming, trying to understand live streaming because there's a fight tomorrow, Eubank versus Ben, which is being live streamed on DAZN, and I got to thinking. Last time Netflix tried to live stream the Mike Tyson Jake Paul fight, it was terrible. And at the time, I didn't have much understanding of why it was terrible. There was a big discussion on Reddit about it. So yeah, today I'm going to be jumping into the Zone Engineering blog about how they do their live streams, how they scale, how they anticipate scale, and yeah, so should be interesting. Let me share my screen, and we'll just jump straight in. Window, entire screen. I think this should work. Cool. I think that should work right now. Cool. The Zone Engineering blog. Can you guys see that? Let me move this to a different screen. All right, cool. I think you guys can see that. If you can't, let me know in the chat. Let me open up chat as well. So yeah, in terms of a recap for what we're doing today, we're going to be diving deep into understanding how live streaming works because the Eubank versus Ben fight is tomorrow. Very highly anticipated fight. Going to be quite interesting to see how that works. And sometimes we take live streaming for granted, like when we're watching a big live stream, like IShowSpeed or one of these live streamers, we take it for granted. We don't actually understand how technically challenging it is. And yes, sometimes when it doesn't go to plan, like with Jake Paul and Mike Tyson, that was in November, a lot of people are quick to criticize and say, "Oh yeah, Netflix should have prepared." But when you're dealing with 65 million concurrent viewers, that's a behemoth. That is like scale on another level. 65 million concurrent people watching a live stream. Do you know how technically challenging that? I think at that scale, the internet is your limitation, like the actual infrastructure of the internet. I don't think you're being limited by Amazon or like whatever cloud service you're using. You're being limited by the internet. So yeah, the zone seem to be consistently doing live streams pretty well. And tomorrow they are live streaming the Chris Eubank versus not Nigel Ben, Conor Ben. Nigel Ben's his father that fought 33 years ago. But yeah, they seem to consistently do it well. So we're going to try to understand how they do it. They have an engineering blog. And like I mentioned last week, engineering blogs are a great resource if you're trying to understand how certain things work and how some of your favorite tech companies do things. I would highly recommend going through their engineering blogs and yeah, just seeing how their engineering teams are uh, solving problems at such scale. I mean, yeah, the zone handles most sport live streaming events. So yeah, they have this one article called "Predictive Scaling: Tackling Traffic Spikes Using Machine Learning." We're gonna read this. Actually, I think before this, it would be useful to understand how live streaming actually works. Because I personally don't know. I can give an estimation or like from my understanding of system design, I can try conjure up something that I think would be correct or I think would work, but I may not be taking certain things into account. So yeah, live streaming, how does it work? Cloudflare, okay. They're a pretty respected company, so I think okay, tech. Okay, it's AI overview. I think if we read this AI overview, we'll have a pretty basic understanding, and that should be enough to get us up and running to be able to read the other Medium blog. So yeah, live streaming involves capturing audio and video, encoding it for efficient transmission, and delivering it over the internet to viewers in real time. This process utilizes technologies like encoding, compression, and content delivery networks (CDNs) to minimize latency and ensure a smooth viewing experience. Okay. Here's a more detailed breakdown. Number one, content capture. Audio and video data are captured using devices like cameras and microphones. This raw data is then prepared for transmission over the internet. Okay, so in terms of like a boxing event, they have cameras at the boxing events to capture content. Number two, encoding and compression. The raw data is encoded into a digital format series. Yeah. Compression techniques reduce the size of data, making it easier to send over the internet. Okay. So they need to encode it in different sizes as well. And because when they're sending it over the internet, people with different devices or different internet speeds may need to view an encoded version, which is easier to actually like transmit to them. So let's say someone's on very bad internet, but they are still connected to the live stream. They won't get like the 1080p version. They'll probably get like a very blurry version. But yeah. Number three, segmentation. The encoded and compressed data is broken down into smaller segments or packets. This helps prevent data bottlenecks and saves bandwidth. Okay. So essentially, they capture the content, encode and compress it, so turn it into zeros and ones, and then chop that up using segmentation. CDN distribution. A content delivery network is a system of servers that distribute the data to various locations around the world. This allows viewers to access the stream from a server close to them. And okay, cool. So they capture the content, they encode and compress it. So I think I should get a whiteboard. Excalidraw. I don't know what that's from, but we'll delete that. So number one, content capture. I don't think I can swear. I had to watch what I say. Okay, cool. Number one, content capture. Number two, it was encoding and compression. Number three was, what was it? Segmentation. So where they chop it up. Segmentation. Actually, I should probably make this bigger. Or zoom in. Do I zoom in? Can you guys see me? Okay, cool. I think you can see me. Okay, how do I move? All right, cool. Let me zoom in because some people were complaining last time that the text was too small. Hopefully this should be large enough. I'll check the video afterwards and see. Okay, so number one, content capture. Number two, encoding and compression. Number three, segmentation. Number four, I think was CDNs. Yeah, CDN distribution. CDN distribution, where they send it to different content delivery networks around the world, and the viewers then would then connect to those CDNs that are closest to them to be able to actually view the content. Decoding and playback. Once the data reaches the viewer's device, it's decoded, meaning it's converted back into video and audio. A video player application then displays the video and plays the audio. Okay, so decoding and playback. decoding and playback. Number 6. What's number 6? Latency and buffering. The goal is to minimize latency, the delay between the streamer and the viewer. Viewers' devices often have a buffer that temporarily stores some data, allowing for smooth playback even if there's a brief connection issue. Okay. I don't think that's part of the process. I think that's just something that's maybe like a nice to consider, you know? Cool. So these are the steps for conducting a live stream. So shall I go into the effort of drawing out a boxing ring? Cool. Here's a boxing ring. Imagine 2 people inside the ring. Okay, let me draw one in a different color. Okay. Okay, how can I actually represent this as a boxing match? Yeah, it's actually the Eubank versus Ben. I think Eubank Jr. versus Ben. Cool. Okay, cool. So here's the fight. Ooh. Okay, so here's the fight right here. We then have a camera. Let me actually put this here. Let me draw a camera. Let's make it black. Looking like this. That is the worst camera ever, but you guys get the point. Okay, cool. I think that illustrates the point well. So we're not trying to do the most here. Okay, so number 1, content capture. So they have a camera that is capturing the content. Now, encoding and compression is when you take this content and encode it into zeros and ones. Let's draw that like this. Let's get some text. 1 0 something like this. How do I make this smaller? I think hopefully by the end of this, we all should have a better understanding of live streaming as a whole. So this is encoding and compression. So we'll label this as encoding. By the way, for the post live stream update, I'll probably make a nicer graphic so that you guys can understand this a bit better. I think this rough version is for the viewers trying to understand how live streaming works right here. So we capture the content live. We encode it into ones and zeros. We then compress it. How can I represent that? Let's group this. And move it like this. Compression. We have now compressed this. I'm not going to win any graphic design awards, so I don't mind. Okay, this is compression. We have made the file smaller. And then next step, segmentation. So essentially what segmentation is we now take this compressed version and we chop it up into smaller pieces that we can then send to all of the content delivery networks that our users are connecting to. So let's break this down into smaller sections. That should suffice. We'll label that segmentation. Segmentation, like that. Now, Once we've segmented the encoded and compressed version of the content, we then send it to a content delivery network or multiple content delivery networks around the world. So this is Earth. How do I make it blue? Yeah, that should be fine. What am I trying to do here? I'm trying to draw Africa. It's like the worst drawing ever. But you guys get the point. That's the UK. If you're just joining the live stream and you see me do this, you're like, what the hell have I joined? But yeah, you guys get the point. This is Earth. This is Earth right here. And there are CDNs around the world. So this is CDN1. Let me change the color. Basically, the point I'm trying to make is, so with CDNs, there are multiple around the world. Let me delete this. And once we have the segmented binary that we are gonna actually distribute to all of the CDNs, we want to send them to all the CDNs around the world. So CDN, that's in Russia. Okay, how can I represent this nicely? I think maybe draw like a little black dot everywhere. One in Russia, there's one in France, one in the UK, one in Spain, one in Morocco. You get the point. CDNs. So now, with these segments that we have, we send them to all of the CDNs around the world. So we send that to there, to etc. You get the point. So now, as a user, as a viewer of the boxing match, here you are. You connect to a CDN using your phone or a TV or whatever device you are using to watch the live stream. So let's say you are in Spain. You are now connected, and the last step in the live streaming process happens where you are decoding and playing it on your phone. So you can imagine if you're doing it at the scale that Netflix was trying to do it at, 65 million concurrent users, this process that we have just described becomes very, very costly and there are a lot of bottlenecks. I mean, managing 65 million concurrent users has a lot of issues with it. And we saw that when they tried to do it. So now that we understand how live streaming works at a very high level, let me label this quickly. Live streaming. What should I call it? Live streaming, very high level. This is like the highest level. I think the level higher than this is saying, yeah, just connect to the live stream, bro. But yeah, this is live streaming very high level. So let me just recap that once more. So we have the event that we are trying to live stream being captured by the cameras at the event. This is then encoded into ones and zeros, which is then compressed so that it's smaller. It's then chopped up in the next process called segmentation. All of these individual segments are then transferred to the CDN, which is the content delivery network around the world. You as a user will connect to the CDN server that is closest to you, and you will start to decode and play back the live stream. So this is live streaming at a very high level. Now, once it's not just you and it's millions of users watching the same thing, this is where it starts to become a technical challenge, and scalability considerations have to be taken into account. So I think the best example of someone doing this right now at a very high level is DAZN, and they've written an interesting blog post called Predictive Scaling, Tackling Traffic Spikes Using Machine Learning, that will allow us to understand how they do it and probably gain some insights. So yeah, let's just jump straight in. Live sports streaming comes with a lot of challenges. One major challenge is being able to handle large traffic spikes just minutes before an event starts. Usually this can be achieved by scaling the infrastructure, but this is very inefficient and costly. So essentially what they're saying is before the event starts, everyone connects, and you need to be able to handle that. So like before the event starts, no one's on it, because who's going to be joining a live stream before the main thing, right? But as soon as it starts, as soon as the bell rings, you're going to see a spike in traffic, and you need to be able to account for that. So uh, what they're saying here is usually this can be achieved by overscaling. So they're saying one way that we could have done this is we could have spun up all the servers that we think we need, but they're saying this is very inefficient and costly. So they they have obviously solved it, and they're going to tell us how they solved it. So using an internal tool we call Smart Scaling, created by Site Reliability Engineering team in collaboration with predictive models created by our applied machine learning team, we have created a way for our engineering teams to scale the minimum capacity of the servers automatically. The service is written in Go, and the UI is created using React. A Terraform module is used to create scaling adapter that enables services to scale by including this module. We use AWS Cloud primarily for all our infrastructure. Okay. So here they're just going into detail about the tech stack used in their service. Okay, how it works. The smart scaling service is made up of 5 main components: ingestion, API, UI, delivery, scaling adapter. Ingestion. The AML team trains the prediction model per territory, outputting daily the next 7 days of predictions. These predictions are in JSON format and fed into ingestion S3 buckets, which triggers a Lambda function to insert the data into the API. We have alerting in place when our prediction data points have less than 3 days of data left to catch any problems with ingestion. This gives us enough time to react and fix the problem while still being able to predictively scale, albeit with less accuracy. Each new day of prediction data is more accurate. Okay. So essentially what they have, or what they're trying to describe here, is their ingestion pipeline for prediction data. So they are trying to predict over the next few days how many servers do we need, basically. And they put these predictions into an S3 bucket, and once something is dropped there, they trigger a Lambda function, which then sends it to a database. Okay. The API at DAZN, we have great belief in democratization of data. As such, we make sure that every API that we create can be accessed by all of our engineers. Every API that we create uses HMAC with HashiCorp Vault for programmatic access and Azure Active Directory authentication for user access. Okay, so they're saying this API for smart scaling can be accessed by everyone in the company using Active Directory. HMAC with HashiCorp Vault, I don't know what that is. What is that? HashiCorp Vault uses SHA encryption to hash sensitive data and order logs and transmit secrets engine. Okay, so it's like I think the equivalent in Microsoft Azure is Key Vault. So basically, they're storing secrets in there for being able to access the API. So that, yeah. So they're doing defense in depth here. So doing 2 layers of security. So using HMAC with HashiCorp Vault and as your Active Directory. So you need to be authenticated and you've got to have the right keys to be able to access this API. Nice. As seen in the above screenshot, the API supports different metric types. Currently, we focus on concurrent streams, but in the future, we plan to introduce other prediction metrics such as sign-up members. There's also different prediction models available. There's upper and composite predictions available. Upper refers to the upper bound, and composite refers to a combination of the upper, middle, and lower bounds that make up the resulting prediction. This model tends to be a more accurate one. Let's have a look at this. Okay. So what they're saying here is this is the response of the prediction, and it's saying, I think at this timestamp in Japan, we expect the lower bound of concurrent streams to be this thing that they've blacked out. The upper limit is this other thing that they blacked out, and the actual is obviously something that they have in their training data set. Okay, let's see how they use this. Okay, UI. This is the front end to help visualize the predictions. It also allows for creating overrides by certain select individuals as the predictions are not always accurate, and there needs to be a mechanism to allow live changes. If the zone is launching a new offering, it may not be part of the prediction model by this time, hence overrides helps with this. Okay, so this is how they visualize the JSON predictions in a graph like this, and they're saying certain users have the ability to change the predictions by using this UI. Why would they override those predictions? We'll see now. Can be noted that the AML team also provides actual data against the prediction. The numbers in the chart are redacted as it's information sensitive. From the above image, also it is clear that predictions are perfect. As such, smart scaling is designed. Okay. So essentially, what this graph here is showing, let me zoom in so you guys can see. So what this graph is showing here is the actual live concurrent users is in red, and what they have predicted is in green. So what they're trying to show here is the prediction fits the actual data basically, and sometimes they overshoot, but I think overshooting is better than undershooting, if that's even a word, because if you have more actual viewers and you've predicted you're going to have less, then a lot of users will have an unsatisfactory experience. But if you overshoot, that means that everyone who's actually viewing your stream, everyone's going to have a pleasant experience. And that's what you want. With something like this, you don't want to undershoot, if that's even a word. I don't even think undershooting is a word. The opposite of overshooting. You don't want that. And so, yeah. So this is an example of when you predict something to be higher than it actually is, it comes with some benefits. Yes, it will obviously cost more, but no one's going to have a bad experience. And in terms of your reputation, no one's going to be able to say anything or like, yeah, this is not going to tarnish your reputation or your image. So this is pretty good. Okay. It is noted that the AML team also provides actual data. Okay, we just said that. The numbers in the charts are okay. From the above image, also, it's clear that predictions aren't perfect. As such, smart scaling is designed to only change the minimum capacity of a service. More on this scaling adapter section. Okay. When deciding how the predictions could be consumed by the services, we had to come up with a solution that was scalable. We decided that requiring the services to have a sidecar that pulled the API was not efficient in the long run. Let me read that again. I didn't understand that. When deciding how predictions can be consumed by services, we had to come up with a solution that was scalable. Okay, so they're basically saying we can't just keep hitting this API and getting back the data. We need something more efficient. Okay, makes sense. We instead decided that we could use an SNS topic with a message notification at regular interval. The interval was 10 minutes, as that matches the resolution of our predictions. We chose SNS because it's consumed by different many tools. It's just like a standard message queue. SNS topic. Amazon SNS message. Okay, so it's something specific to the Amazon ecosystem. So that was first create topic and then. Okay, so yes, standard message queue. If you're subscribed to the Road to 10x System Design, I'll be covering message queues at a later stage. I think it's like week 8, week 8 or 9. I do cover message queues, but yeah. As we want our data to be open for everyone to use, we made sure that this data was sent to many different places. Some teams could directly access the SNS topic, doing whatever they wanted with the prediction for their own purposes. Our scaling adapter also consumes this message. The data is also sent to New Relic and to CloudWatch, where other metrics can be compared against prediction data to find any correlations. Okay. So basically, they subscribe to the topic, and every 10 minutes they get back a prediction about how many servers they need. And this is then going to be sent to the scaling adapter, which is what we're going to read now, to understand how they actually scale the infrastructure. So let's read on. It was necessary for the zone engineering team to have an easy way to integrate with smart scaling to make adoption quick and painless. Considering all of our teams already use Terraform and AWS, we decided that a Terraform module would be the right tool for the job. Okay. For those of you that don't know, Terraform's infrastructure as code. So you basically define your infrastructure in Terraform. So that's what they're doing here. They're saying they need a Terraform module so that when they get back the data from the API for their smart scaling predictions, they will then spin up more or less servers depending on what they need. Cool. The module creates a Lambda function that is triggered by the SNS message that is sent every 10 minutes via the delivery service. This Lambda function is configured to scale a single ECS service based on configuration that is chosen specifically for that service. The module allows for certain configuration parameters such as which metric model to scale from and how many tasks should be created per prediction metric. Okay. The Lambda function affects the minimum capacity of the ECS task only. This is because smart scaling is designed to only be used as a scaling head start. Okay. Auto scaling based on other metrics still needs to be implemented to help the service scale beyond predictions, which is also important for a service to be able to scale on its own without smart scaling in case something goes wrong. Okay. Let's read on. Maybe that'll make sense. When using the module, a dashboard is created per service. This dashboard gives some metrics around the scaling activities performed by the adapter. Also shows some scaling efficiency metrics which describe how close to the prediction the service is running, and ratings gets lowered if more tasks are actually needed to serve the current traffic as possible. Okay. I think this is starting to make sense. If this doesn't make sense to anyone, I will be giving a brief overview in the live stream wrap up that I do. I'll be writing a short like blog about this because this is some interesting shit. I don't know if I can swear. But yeah, pardon my French. From the above screenshot, the contents of the dashboard can be seen. Context describe the following. Current configuration that the adapter is running with, charts with numbers scaling event, scale up and down, prediction number, investment. Okay. Currently, the solution works well on getting ahead of traffic before it hits the platform. The prediction are not always accurate, but even getting halfway there, in most cases, allows auto scaling to handle traffic more gracefully. Having to double capacity is much easier to achieve than scaling tenfold or more. Dynamic configuration. Some of the issues are that configuration, static configuration change require Terraform apply to be run. Configuration should be dynamic configurable parallel to that needs to run Terraform. This allows teams to create more efficient. Okay. One limitation with the service is that there's currently only one type of adapter, which is ECS. Other workloads such as Lambda and Kinesis Streams. Don't know what Kinesis Streams is. What is that? And yeah, if you're a junior engineer watching this, whenever you read something and you don't understand something that, sorry, let me rephrase that. If you're a junior engineer and you're reading an engineering blog or some documentation and people are throwing around buzzwords or names of specific technologies that you may not understand, always Google it or ask ChatGPT or ask Claude or your favorite LLM. Understand what people are talking about. If you don't, you will you'll go through life not understanding anything. So an example here, like kinesis streams. I don't know what that is, but I need to know to be able to understand what they're describing. And yeah, so it's something specific to the Amazon ecosystem. And yeah, I mean, that's not from a lack of understanding, that's from a lack of experience using AWS. I've never used AWS, so I would never know what Kinesis data streams are. So yeah, always do that. That's my top tip of the day. Um, benefit from smart scaling to preemptively adjust their configuration to better handle spikes in traffic. Conclusion: with the help of our very talented AML team in collaboration with the site reliability team, DAZN has achieved, albeit not without flaws, but a very serviceable way of predicting traffic to give users better user experience by scaling in advance. This solution is much cheaper and more efficient than scaling services manually before big events, and it is also automatic, which allows engineering teams to spend time on features and improvements rather than worry about scaling. Okay, cool. So I think I have a pretty good idea of what they're doing here. So using my handy diagram, I will try and explain how DAZN tries to predict scale. So DAZN have a large training data set of how many concurrent viewers were at previous events. Using this, they are able to then predict how many concurrent viewers are going to be on their next live stream. So let me give you an example. So let's say they live stream a UFC event. They know that the next UFC event will most likely see the same amount of viewers. They're able to predict at certain times in different parts of the UFC fight how many people will be viewing. And just before they hit the peak number of viewers, they preemptively load up more servers to be able to account for that peak in traffic. So essentially, they're using machine learning to predict how many viewers are going to be there at a certain time. And using that information, they're able to scale, what's the word? Elastically. Yeah, I think scale elastically so that users can have a good experience. Now, the alternative, or what they were probably doing beforehand, is they would say, all right, cool. How many concurrent viewers are we expecting to be there at peak time? And they would spin up as many servers as needed to be able to account for all of those peak viewers. So let's say they predicted or they anticipated that Eubank Jr. versus Ben is going to have 10 million concurrent viewers. If they didn't have this machine learning team that built this predictive scaling tool, they would spin up as many servers they can to be able to handle 10 million concurrent viewers seamlessly. So number one, that is very inefficient. Number two, it's very expensive, because what if 10 million concurrent viewers don't come? Then you've just spent a bunch of money for no reason. So what they did instead is they use machine learning to try and predict at certain times how many concurrent viewers are we going to have, and just before it reaches those certain peaks and troughs, they either scale up or they scale down. So that's how they do it. And yeah, I hope you guys found this beneficial. If you did, you can join me next week again for another live stream. And yeah, subscribe to my newsletter. There's 2 newsletters now. There's one for system design and one for advanced level Python. Subscribe. I post 4 times a week on my LinkedIn, 4 long form pieces, and I post every day. If you find it beneficial, I would sincerely appreciate if you guys could share, could let other people know. Everything's free. I'm not charging for anything. Like, everything's free. And sometime soon I might be doing giveaways. So yeah, get ready for that. And yeah, I think I'm going to wrap this up. For those of you that did join, I sincerely appreciate it. Sorry I was not able to respond on chat, but yeah, it was a great experience. We learned a bit about live streaming, and I'll quickly make the live stream recap, and I'll post it on my LinkedIn in about an hour's time. And yeah, I'll see you guys next week. Take care. Bye.